how the benefits outweigh the new technology investment. Thank you for joining NTMA's technology team today. We value your time and promise to start and end on time. And as Kelly just mentioned, if you haven't already done so, please enter the audio PIN number that you received as you signed in, the format pound, PIN number pound. That'll help us eliminate any audio distractions. This is the first of 2 webinars on 5-axis machining. In today's webinar, we will give a high-level overview of the topic, explain some of the 5-axis terminology you've likely heard, and you'll also learn about the advantages of using the 5-axis machining. In the second webinar on March 22nd, we'll delve into the high-speed and high-performance aspects of 5-axis machining. When we're finished, you'll be fully equipped with the information necessary to make an informed investment decision. We're honored to have Gisbert Ledvan from GF Machining Solutions and Bill Vanovic from Grobe Systems presenting our webinar today. Gisbert completed his tool and die apprenticeship in Germany back in 1983 and has been involved in many different industry-specific roles over the past 23 years. Gisbert moved to the U.S. in 1993, and he is now the Director of Business Development at GF Machining Solutions in Lincolnshire, Illinois. Bill Vanovic is the VP of Universal Machine Sales for Grobe Systems. Bill started his manufacturing career as an NC programmer, and for the past 30 years, he has held a variety of engineering, new product development, and VP positions with several of the major machine tool builders. Currently, Bill guides the development of 5-axis machining centers, automation systems, and software at Grobe Systems in Bluffton, Ohio. Both Bill and Gisbert also serve on NTMA's technology team. If you'd like to ask questions, please use the chat box function on the GoToMeeting screen and be sure to send to all. Our presenters will answer the questions at the end of the webinar. So without further delay, Gisbert Ledvan and Bill Vanovic on the business case for 5-axis machining. Men, thanks in advance for educating us.
Thank you, and good afternoon, everyone. If we could advance to slide 3. Investing in 5-axis machining centers makes sense with the proper strategy. Saving time on existing parts, increasing spindle utilization, reducing the number of machine tools, fixtures, and tools can improve your existing process. Financial considerations include the upfront cost of investing in the new technology. This not only includes the price of the machine tool, also the software, tooling, workholding, and quality systems that go along with that. And a very big focus will be on training. This could be a brand new concept for many. Compared to the potential return on investment, the ability to produce complex components has a high potential to reward manufacturers of high-value customer contracts. In the case of critical components, the buyer may also be less price sensitive. As we get into this type of equipment, your competition really goes down. If not for the job itself, for the potential improvement in process, allowing you more competitive pricing and better accuracy of your parts. Case of critical components, the buyers may also be less price sensitive, of course. There are usually fewer manufacturers. Market considerations include the opportunity to diversify into a growing industry segment like aerospace and medical, with the ability to manufacture those in-demand components. Would expertise in 5-axis machining allow your shops to get more work from existing customers, find new customers in the same work segments, or diversify into new contract segments? Business case for investing in new technology should be carefully considered. Next slide, please. To find the most suitable opportunities for your shop, consider the size and weight of the part families you're working with, what materials, what level of accuracy needs to be held, and where do these characteristics favorably overlap with your existing work. This example customer specializes in complex 5-axis parts that he says fits inside of the blue box, which is kind of below his bench right there. In other words, he has a clear idea of the part size and type he will compete for. and pairs his capability for testing and quality certification, focusing on aerospace and defense. Next, please. These are typically the type of industries where 5-axis tend to shine. Aerospace, either rotating part or structural part. Gas and oil industry, we show basically as a 5-axis, what you would call 3+2 work, where there may not be a lot of 5-axis sculpturing, but the complex compound angles required to manufacture these parts can really simplify the manufacture if you can do it in a 5-axis environment. Medical, on a small end machines specifically, tend to be very complex shapes and very tight tolerances. And then, of course, automotive first and second tier. High utilization of 5-axis machines, mostly for positioning and, again, holding accuracy by reducing setups. Next, please. The advantages of 5-axis machine: ability to save time. Machine complex shapes in a single setup. This combines more efficient cutting and more operations in one handling of the part. Much greater machine productivity compared to multi-step setups on a typical 3-axis mill, considering how much faster it would be to drill holes on multiple compound angles without changing the position of the part in the fixture. This translates directly to fewer labor hours, changeover costs, which all relate to overall cost savings. Improved quality. The less times you handle and refixture a part, being able to do more work off of a single datum point will increase quality. Fewer setups, improved dimensional accuracy. No human involvement, which can cause incorrect alignment or scrap parts. The general approach to 5-axis allows the use of shorter tools. Shorter tools reduce vibration and create higher quality of surface finish. High quality surface finish can eliminate secondary process, as in hand finishing. 5-axis capability also supports new workpiece designs like undercuts, small fillet radius, and sharp edges and so on. Reduced tooling and fixturing and material inventory. This requires a whole different view of manufacturing your parts. Many times you'd want to try to use sacrificial material where you can do more of the part than one handling and maybe snap it off at the end. Dovetail style fixturing. So it really requires an open-minded approach to how you're holding your parts and the best utilization of handling the parts. Improved production flow. More flexibility in these fewer machines are needed, often reducing capital investments and requiring less production space. No need for intermediate storage of parts between operations, and fewer parts to be reworked due to quality improvements, which all improves cash flow, faster process throughput, shorter lead times, less money sitting around in semi-finished products, being able to produce small batches more cost effectively. Next, please. A little bit of a concept of even on work that might be done today on a 3-axis mill, the advantages of going to a 5-axis mill. On the left-hand example, rather than having to sculpture and ball nose and overlap, which is a very time-consuming process on a 3 or 4-axis mill, the ability to simply tilt the spindle and more effectively cut that surface can be a huge advantage. You'll get better surface finish, reduced cycle time, and typically better accuracy. In the right-hand example, I'm sure you've all run across a situation where you have a radius in the bottom of the deep pocket, which always requires a long cutter, very slow feed rates, and tends to chatter quite a bit, requiring a lot of hand finishing. Just having the ability to tilt the cutter in relation to the part, work at the point of tangency instead of the center of the cutter, shortens up your tool, and again gives you much better metal removal rates. Next, please. Elimination of fixturing. In the left-hand example, the ability to work on a surface directly rather than having to take the part off, refixture, and mount to do an angular surface. In the right-hand example, instead of going in with expensive form cutters, again, the ability to tilt the spindle and cut a surface normally can be a huge advantage to accuracy, surface finish, and production time. Next, we're going to visit the different styles of 5-axis machine that you may run across. Typically, they break down into 3 styles. We have the forked head machine, which is going to take your 4th and 5th axis into the spindle itself. This type of machine normally can accept the most weight on the pallet. Probably one of the big advantages. No weight limitation whatsoever since you're running with basically a flat table. All of your joint work happens in the tool. One big concern with this type of machine is you're typically going to look at a machine that has 2 to 3 times the stroke of your largest work part. If you consider the orientation of the tool, if you want to do side work, you have to account for the length of the spindle and the length of your cutting tool, both to the left, the right, the front, and back of the part. So again, this typically requires a lot of stroke. The more stroke you have for any given part size will tend to go against accuracy. So it's a good style for very heavy parts, maybe not the best solution for typical smaller 1 meter or less parts. The center section gives you a little bit of both. It gives you the A-axis in the spindle and the B-axis on the table. You still have the same consideration where you might need a larger machine to access the left and right of the part. You won't have as much weight as the fork head example, but it's going to be more weight than a double table. Again, a lot of axis motion for potentially a very small part would be the downside to this configuration. The third, maybe the most typical configuration, is a double rotary table, where the spindle is typically a Z-axis, and both of your rotations happen within the table. This will give you the least axis motion for any given shape, usually very quick response times, and it has the least impact on tool versus part. So for most applications, we feel this is maybe the best solution as long as you don't have a very heavyweight part. Next, please. Under the considerations of how to go about doing this, if you're coming from a 3-axis world, in the top example, typically you bring your tool down, touch it off the surface of the part, reference that as 0, and effectively all the rest of your tools are going to be plus or minus offset from that point, or you'll just set your offset by touching off the tool in each part. When you get in the world of 5-axis, center of rotation is the most critical consideration. So in this case, everything that's coming off of the tip of the tool. Normally, this is going to require the investment of a presetter or the time it takes to maybe laser preset the tools in the machine. But it's absolutely critical for the final result and the accuracy that the center of rotation of your table is the known distance to the tip of the cutting tool. Very critical. So we're looking at machine 0 to workpiece 0 to reference point, which is the tip of the tool to the work part. Next, please. And here's an example of how that translates. The machine is always tracking the MCS, which is the machine coordinate system. This is basically the cutting tool to the center of rotation of the machine. From there, we translate the machine center of rotation to your workpiece part 0. Any 5-axis machine you look at will have the capability to process this internally. So we're not dealing with a lot of math here, especially in a 3+2 application. You can simply program from your datum 0 on your part print and let the machine's CNC control do the calculations to bring it back in. But again, keep in mind the machine center of rotation to the workpiece 0 is a very critical setting which normally is overlooked in a 3 or possibly even 4-axis scenario. Gisbert, you want to take this one?
Yes. So, good afternoon, everybody. Now it's afternoon everywhere, I guess, except California. I want to talk a little bit about the terms and information you will receive, or when you talk to your operator, or when you talk to somebody who's in the 5-axis machining business, when we talk about kinematics. And these kinematics are very important, as Bill pointed out, in order to make sure that your machine machines the part accurately, and you need to know the terms of the different axes, because now you're not only dealing with X, Y, and Z, now you're dealing with additional axes. And there's a certain norm established when you're talking about different axes. The C axis goes Z, the B axis turns around the Y axis, and the A goes along the X axis, around the X axis. So if you talk to somebody when you want to turn the part or you rotate the part, you know exactly what you're talking about. And again, it's very critical that your kinematics of the machine are established. So when you reference your rotary table in relation to the Z, X, and Y axis, the machine needs to be calibrated so when you run your program that the machine tilts in the correct fashion so you maintain the accuracy to your zero wherever you decided that's going to be. There are different types of machines. We'll give you some abstracts on the different types of tables here. One part you see on the left-hand side is a high-speed milling machine. And one thing is very critical. If you look at the rotary table here, the zero line of that part is around the rotating point of the table, what gives you maximum accuracy. You also see that the distance between the z-axis and your table rotation here is very close. So you can maintain maximum accuracy in such a design. So if you have smaller parts, you should look for this. Also, make sure that you have on the efficiency side that your tool changer is very closely mounted to the work area. That also means when you laser your tool in relation to the table and to your z-axis, you want to make sure that that laser measuring device is as close as possible to the axis so you maintain maximum accuracy of your tool and your kinematic. Here's another example on the right-hand side where we see a larger machine, what then can handle bigger parts. You have a trunnion type table here. What is basically giving you similar features. Obviously, the machine is maybe not as dynamic because it's going to handle bigger parts, but you have, again, the same orientation of the axes and the table there. Bill, back to you.
Along those same lines, if the machine is a vertical spindle or a horizontal spindle, as Gisbert just explained, the alignment of the axis are always the same. Your A axis is going to rotate about the X, the B axis is going to rotate about the B, and the C axis will rotate around the Z axis. In a horizontal spindle application, having the ability to retract the spindle out of the work zone allows us to work with a full work cylinder and a long diameter tool without interference. This is always a consideration in a 5-axis machine. You have a certain work cylinder that you can work within. Whatever tool you put in the spindle many times can eat into that work zone, so you have to very carefully consider length of tool versus part versus access point. The other advantage we feel to a horizontal is, as with the 4-axis horizontal, you have gravity working to your advantage. As you're working on sculptured surfaces, you're not piling up chips within the bowl of the part, and you're not recutting the chips. Okay. Next. Another advantage we feel with the horizontal spindle, from the center of the pallet gauge line, which is the top representation, to the full retract of the gauge line of the spindle, the distance from the front bearing pack to the spindle gauge line remains the same. We're not giving up any rigidity as we get closer to the part. Next slide, please. On a vertical spindle machine, typically you're going to have a ram type scenario, something to really consider if you're dealing with very small parts. When you're fully retracted, you notice we have an extension of 200 millimeters from the bearing pack to the gauge line of the spindle, but as we extend the spindle closer to the pallet, that dimension is now 715 millimeters. So we end up with a little bit more of a leverage effect, and also you notice the spindle is always in the work zone. So again, as you put a longer tool in a spindle, it's getting into your maximum size part, being able to cut within the pallet. Just an example of the long tool, big work cylinder. With the ability to retract the spindle completely out of the work zone, we can do a part that's pretty much the full size of the pallet, access all sides of the part, and not have to worry too much about interference. Okay.
So now we're going a little bit away from the machine, and we want to educate you a little bit about the whole process and some terms you will find, and most of you probably already know these terms, but I think I want to bring them up because you might deal with some engineers who are not so familiar with with the manufacturing process. And I think it's very critical when you go from 3-axis to 5-axis that you take certain things into consideration. What we're going to talk about here is the blue area where we're going to talk about planning, analyzing, and looking at the design. And then we go into the lower case, what I call that, where we implement, we do some testing, and we're going to make sure we do certain maintenance on the machine. CAE, computer-aided engineering, so that's really your design work. Make sure that you get the right files, that you get clean files, that they match each other, specifically when you are going into full 5-axis, what we're going to cover later. But in the 3+2, it's also critical that you get clean data. Then your CAD data, computer-aided design, and then your CAM data. So that's more where you program your machine, where you set the tool paths. You want to make sure that your CAM system is really up to snuff and can deal with all the specific features of the machine, the specific G codes, if that machine is using that, because not every CAM system is necessarily tuned into 5-axis, and you might not be able to take full advantage of all the features that machine offers you if you don't have a suitable CAM system. So make sure you look at the right stuff and look at that. Then case tools, computer-aided software engineering. Those are complex software systems. And then last but not least, the CMM machine. You do a test of the part where you want to inspect the part, and when you want to do really accuracy and you want to recalibrate your machine, I would say you should have something like that in your shop, or have the capability to go to somebody to utilize a CMM to calibrate the part before you go into a mass production. And here are a couple other components you need to take in consideration when you go into the 5-axis machine. First of all, you got to look at your material. Are we dealing with aluminum, copper, brass, graphite, whatever you machine, alloys? Make sure you take that into consideration, because it's also going to determine what type of cutting tools you're going to use. And certain cutting tools are more suited than others. Specifically, if you go into more complex 5-axis, full 5-axis applications, you can get really high performance tools, what are maybe looking for some of us a little strange in the beginning, but there's a lot of benefits to these tools when you go into the 5-axis application. Also think about your cutting process. Make sure that when you use a CAM system, that your tool path is perfectly aligned with your machine capabilities, and that your CAM system gives you the right post and the optimum tool path, because you don't want that the machine does a lot of air movement and you're not cutting any chips, you're not standing in front of the part, you're not having the right feeds and speeds, so you wear out your tool faster, you're losing inaccuracy. So make sure you have a really sophisticated CAM system and a good post processor for that. And then last but not least, not really last, but the workpiece holding. Take that really into consideration. How are you going to hold your piece? Specifically, if you want to do 5-sided machining, you want to hold the part in a certain area what is maybe not critical to the accuracy. So you have like a dovetail application where you can really get as close as possible to your surface finish to maintain the accuracy and hold the part very solid in these 5-axis motions. Or you have to go to a vise, but then you need more material to reach all 5 sides. And then one critical component is certainly your machine tool. Consider what you do, what type of work you do. Are you looking for smaller parts, bigger parts? You want to get better surface finishes. You want to have high accuracies. That certainly plays into your consideration of your machine tool. You need to make sure that you have vibration damping capabilities on the machine, that your temperature is stable so that the machine is not growing or shrinking on you depending on the temperature changes within your shop, so you can maintain a full 5-axis benefit or benefit from the full 5-axis and the accuracy of a 5-axis application. So the perfect integration, really, we talked about the material a little bit. Think about your tool material, what your cutting edge geometry should be on your cutting tool, and then also design for high speed and high feed and high performance. Depending on what you do there, you might use solid carbide tools, you might use insert tools when you want to remove more material. If you want to get good surface finishes, good accuracies, you might want to have a minimum chip load on your workpiece, on your cutting tools, so using carbide tools for high-speed applications to achieve that. Machine base, it should be a robust construction. You got to also consider what specifically when you get into high-speed applications, let's say more than 30,000 RPM spindle speed. If that cutting tool breaks, you better have a good cabinet around it so that your operator doesn't get hurt. So you got to look at the entire product also on safety. It's a big concern here because when things moving around, make sure that everything is closed. It's a closed cabin so that these tools don't fly through the shop and kill somebody or hurt somebody. The CNC control is also very critical. If your CNC is not going to keep up with the 5-axis data because you're dealing with much more data now, your machine will not be able to keep up with the load of data what goes to the machine. The machine will slow down. It stops even to a certain degree that could break your tool, and you could get marks on your part, and certainly you lose accuracy and surface finishes. We talked about tool clamping and coolant management. Also think about that. Specifically, if you have a 5-axis part and you turn that part in different directions, you want to make sure that your coolant can go there so you can cool your workpiece and your cutting tool, and make sure that that machine allows you to do that, coolant through the spindle. Maybe when you drill deep holes in 5-sided applications, you want to make sure you have enough pressure to get the chips out of those holes. And like I said before, make sure your machine is thermally stable, and your shop needs to be thermally stable because the machine will not compensate for 20, 30 degree temperature swings. And as I said before, on the kinematics, that is very critical because if anything is off between these axes to the table, you will lose your accuracy and the machine will not position to the point where you need to be to cut the next operation on your part. CAD/CAM systems, we talked about that. I also recommend that you get a verification system. What is after your CAM system? So you basically create your toolpath and then you run the entire process through a simulation software. Ideally, you have a machine, full machine you have on your floor in that simulation software, so you can simulate the part, your tools, the table, the holding devices, cutting tools, and you can see that you don't have any collisions or near collision situations when you run this part. So it's very critical that you do all this testing and verification before you send the program over to the machine, because if you start moving stuff around and the 5-axis is moving, operators maybe get scared and they think they have a collision. So do all this verification beforehand, otherwise on the machine you're going to waste a lot of time and productivity. And then on the workpiece, make sure it's a solid hold workpiece. Your clamping and fixture is solid and accurate. If you're working with automation, use a palletization system what can repeat within a couple microns preferably. If you can preset parts outside the machine using a CMM, that will help you a lot with saving time on picking up a part with a probe if you don't want to do that in the machine. And make sure you have enough stock, so like we said before, that you can reach on all 5 sides of the part and you can machine and utilize the 5 axis. on all that. So if you do all this and you take all this into consideration, what we found over the years is that you can at least get a 20% higher tool life, what turns into 0.6% less manufacturing cost, and you can get up to 20% higher material removal rates, what also increases your manufacturing cost, decreases your manufacturing cost by 15%. So Bill, you going to come back on this?
Okay. As you can see in the slide, this is probably one of the more intense examples of true 5-axis sculpture machining. Along the lines of what Ginsberg said, this type of work requires a very high-powered processing, very rigid machine. Also, obviously, this part cannot be programmed manually. So complex tool paths require very powerful controllers. You need to choose a CAM provider that has expertise not only in their software, but in working with you to develop your post-processor to give you the most efficient geometries. Training should include solid models, creating the tool path, and simulations. Simulations may be the most critical piece of the puzzle. In a 3-axis and a 4-axis world, it's not too hard to visualize where the cutting tool and where the tool holder is going to end up in relation to your work part. In a true 5-axis world, it can get a little bit abstract, and you may bang into holders and things that you wouldn't expect. The simulation software is a worthwhile investment that can save you lots of time, money, and potential crashes. Next. Here we just have a little video just giving you an example of the kinematics of the machine, different angles you can approach the part from. As you're watching this, keep in mind, this is where you want to start opening your mind to the way you hold your part and the way you attack your part. This piece can obviously be made on a vertical machining center in multiple handlings. The ability to effectively complete this piece in one operation with the snap-off tab on the bottom is the key to success in the 5-axis world. Overcoming the learning curve, if you're getting into this technology for the first time, is absolutely the most critical area to succeed. I would strongly recommend taking advantage of the manufacturer's factory training courses for maintenance, operation, and programming. When you assign your operators to this type of equipment, if you're not in that market currently, you may want to consider using someone other than maybe your most skilled operator. Many times, finding somebody who's a little more open-minded, not committed to a current way of making things, and more flexible to try new things and accept new ideas has been very well received. Also, if you take a look at the center section, we have a customer who basically has a cheap little 3D model machine, and he will produce his complex parts in plastic. When it comes time to program, rather than having to work with a 3D model or a 2D blueprint, having the ability to hold the part in your hand, look at the orientations, look at maybe new ways of holding and attacking that part can be very, very beneficial. Next. Gisbert?
So, really coming a little, almost to the end here, and I think we want to summarize a little bit about the 5-axis technology you should take into consideration. Look at your customer. Look at what the customer's needs and manage his requirement. Maybe you can help him to look at the different approach, how he makes his part. Maybe you can give him new ideas how you could machine a part a certain way, utilizing the 5-axis, what makes it easier for you to hold the part. Maybe you can save some material. If you can help him with the product development, give him some ideas, be a partner with him. differentiate yourself from your competitor. Somebody with a 3-axis machine will not be able to do certain things. If you can help this customer to develop a certain product a certain way, there maybe is only the way to do that with 5-axis, and then he is forced almost to come to you to machine that part with you because you're helping him to be more efficient to make a part. Integrate the process design. Also take into consideration what cutting tools can you use, how are you going to program this part, what is the best way to hold the part so you don't cut off material and create vibration in the part because you're holding the part too long or too and your tools are too long or too short. Also manage the cost from the start. Look at what are the best cutting tools you should use for this. Is it really always necessary to go with expensive insert tools, or is it better to go with solid carbide tools in certain applications to be more effective and more efficient and accurate without doing additional operations on that part? As I said before, involve also suppliers and subcontractors into the process. All these tooling companies out there, they have very good information to give you on the cutting tools, on the feed rates, what materials can be cut with certain cutting tools, what are the most efficient and best feeds and speed. So take advantage of that information when you design your part, when you program, so you really take advantage of the 5-axis and also the technology in the cutting tools. Integrate your CAD/CAM system. Make sure you have the right tools. Don't save a couple $100 on a CAM system because you're going to waste hours and days and weeks and months to run your machine in full 5-axis mode if your CAM system is too complicated to program 5-axis. You might have to step up and make an investment to buy a better CAM system and a simulation software. And don't forget to train your people, because if they don't know how to use that system, don't expect them to jump from a 3-axis right into a 5-axis application. Simulate products. Make the simulation like I said before. Be creative. Think outside the box. Don't go with your old-fashioned, I'm going to hold this thing in a vise and I'm going to clamp it another way and I drill from this side and I put it on that machine. Think outside the box. Be creative. Say, I just want to hold this part in one location and I want to reach it everywhere and I want to finish the entire part when it comes off the machine. I just have to finish one side and think about that.
Bottom line, the trend towards multi-axis machining will continue to grow to the clear advantages. Companies benefit from less competition. Not every shop can produce complex parts and complex and sophisticated parts. Parts that have fewer competitors are able to deliver higher value. This is the trend we see over the last few years in manufacturing. Eliminating your competition, improving accuracy with less labor input for handling parts, and the ability to machine more complex geometries to a much tighter accuracy.
So I think we're at the end of our part number 1. So Mike, you coming back and tell us a little bit more?
Great, thank you. Thank you. We do have one question from Chris. What are the size limitations on a 5-axis machine on the small side?
Well, I guess I can start that off. Depending on the piece of equipment you're looking at, there are 5-axis machines in the market that are designed to work on parts probably as small as 1 to 2 inch cube size. And depending on the brand and the model you're looking at, the other extreme is there's machines out there that are 2-3 meters. So focusing on the size work you're looking at, going back to the example, customers focusing on parts that will fit within this blue container. So that kind of dictates him to a cube, and he's looking for parts within that cube size. Gisbert?
Yeah, I think you can actually go smaller than that. We have a small machine in our portfolio where we have applications in micro machining, I would say within a couple millimeters of size of the part itself. But again, one thing you need to consider on a 5-axis machine, just think about that you probably have to double your travel if you want to reach everywhere around your part. So let's say your part usually machine is 4 inches by 4 inches. Think about that the machine should have at least 8 inches of travel because when you turn your head or you turn the part, you need to have more clearance and move around and make sure that that you see that you can reach the part from all sides, so all 5 sides.
Okay, thank you. Another question, how valuable is the ability to use G54.4?
G codes in general are kind of FANUC, maybe Haas related. When you get into the higher end 5-axis machines, you'll see a trend towards Siemens or Heidenhain controls. They really do not use G code per se. They have the same functionality. It all relates to center point control, maintaining the actual center rotation of your machine to the cutting edge of the tool.
Yeah, I agree. Well, I think on the Heidenhain control, you can still go both ways with G codes or not. But what I said before, be careful that your CAD/CAM system support these post processors you're going to use, support these type of G codes or other codes they're going to use in the control, because otherwise you're not going to be able to take advantage of them. For example, keeping always your cutting tool perpendicularly to your cutting surface, that the machine will always make that movement and make sure you stay on in that certain location. So you got to make sure that your CAM system supports that, and your post processor, what comes with the CAM system, supports that. Otherwise, you will not take advantage of all the G and M codes your particular machine provides you.
And as Gisbert mentioned earlier, there's a lot of processing going on within the control. Not only are you processing a lot of code if you're sculpturing, but the CNC control itself is maintaining the 0 point through full rotation of the machine. There are situations where different CNC controls could have a 20–30% difference in throughput time just based on that processor speed. So I would strongly recommend, if you have a very sophisticated, very complex part, ask for test cuts. Very tough to do a time study on a sculpture. But if you take a benchmark program and you run it through a few different machines with a few different controls, for your application it may become apparent which is the most efficient solution.
Mm-hmm.
Okay. Still time to put a question in the chat box if you would like. Want to go ahead and at least make sure you are aware that this was the first of 2 in our 5-axis webinar, and the second one is going to be on March the 22nd, same time, and so look forward in advance to you joining us on that. And in the spirit of continuous improvement, we would certainly value your input on this webinar today, things that you'd like to see us do to improve. We'd sure love to hear back from you. We will be sending an opportunity for you to provide some feedback. Would love to have that back from you. Help us to do a better job in the future. So thank you in advance for that. And the last slide you'll see there is contact information for Gisbert and Bill, which you guys, thank you. Appreciate what you taught us today and look forward to the next one. Thank you, everybody. Have a great rest of your day.
Thank you very much.
Thank you, everyone.